Out between Mars and Jupiter, there is a region we think we know well. We call it the main asteroid belt, a broad ring of dark, rocky fragments, leftovers from a planet that never formed. For decades, it has lived in our imagination as a quiet graveyard of stone, sun-warmed, dusty, dry. Now picture this. The camera glides through that belt, past tumbling boulders and shattered worlds, until it lingers on one small, potato-shaped asteroid. Its orbit is unremarkable, a stable path between Mars and Jupiter, just like hundreds of thousands of others. At first, nothing happens. The rock spins slowly in the sunlight, its surface worn and cratered. Then, as it moves closer to the sun, something begins to change. Fine dust starts to lift from one hemisphere, like smoke rising from an unseen vent. A faint veil forms around the asteroid, a fragile, glowing coma. Over the course of days, that veil stretches backward along its orbit, becoming a thin, unmistakable tail. This should not be here. Comets, with their glowing comae and sweeping tails, are supposed to come from the icy outskirts of the solar system, from reservoirs like the Kuiper belt or the distant Oort cloud. The main belt, inside the orbit of Jupiter, sits on the warmer side of the so-called snow line, where we expect most primordial ice to have vanished long ago. And yet, this object's orbit is purely asteroidal, low inclination, low eccentricity, confined to the main belt. Dynamically, it behaves like an asteroid. Physically, at certain times in its orbit, it behaves like a comet. We have a name for such hybrids, main belt comets, or, in another commonly used term, active asteroids. They blur a boundary that once seemed sharp, icy bodies out there, rocky bodies in here. Their very existence forces us to ask new questions. How can buried ice survive for billions of years in the inner solar system, shielded just enough beneath rocky crusts to endure? What wakes that ice up, turning a quiet rock into a briefly active, dust-releasing world? And if some main belt asteroids still hide ancient ice, what does that tell us about where Earth's own water came from? In this episode, we will follow these wrong-place comets through the heart of the asteroid belt, uncover how they work, and explore what they might reveal about the hidden reservoirs of water in the inner solar system, including the water that ended up on a small blue planet we call home. Somewhere between Mars and Jupiter, rocks are hiding snow. And sometimes, that snow still remembers how to shine. When astronomers first mapped the main asteroid belt, they imagined it as a mostly dry, rocky zone, shattered remnants of worlds that never fully formed, orbiting quietly between Mars and Jupiter. For a long time, asteroid meant airless rock or metal, and comet meant an icy body from the cold outer reaches of the solar system. Main belt comets overturn that neat separation. Dynamically, these objects are asteroids. Their orbits are stable, nearly circular paths that sit comfortably inside the classical main belt, with semi-major axes between Mars and Jupiter and modest eccentricities and inclinations. If you looked only at their orbital elements on a chart, you would classify them without hesitation as standard main belt asteroids. They are not plunging in from the distant Kuiper belt, and they are not returning visitors from the Oort cloud on thousand-year ellipses. They belong to the inner solar system's stone belt. And yet, some of them act like comets. As these bodies move along their orbits and approach perihelion, their closest point to the sun, astronomers have seen a faint coma bloom around them and a dust tail begin to stream away, gently pushed back by sunlight and the solar wind. The brightness increases, the profile blurs, and a textbook rock suddenly wears a cometary veil. When the object recedes again and solar heating drops, the activity fades, the coma collapses, and the body returns to looking like a normal, unresolved asteroid. This on-eye-off behavior synchronized with distance from the sun is a crucial clue. It points to volatile material, most likely water ice, being heated and driving off dust. To describe this hybrid behavior, astronomers use two nested terms. The broad category is active asteroids, objects on asteroid-like orbits that show comet-like activity of any kind. Within that, main belt comets are the subset where the best explanation for the activity is the sublimation of buried ice, rather than a one-time disruption such as a recent impact or rotational breakup. In other words, all main belt comets are active asteroids, but not all active asteroids are true main belt comets in the volatile-driven sense. Specific examples make this more concrete. Objects like 133P Oelst, Pizarro, and 238P Arid follow orbits that place them squarely in the main belt, yet they have repeatedly shown comet-like dust emission near perihelion. The fact that activity recurs at roughly the same orbital phase over multiple apparitions strongly suggests an internal reservoir of ice that is exposed or reactivated as the surface warms, rather than a one-off collision that simply ejected a transient cloud of debris. In some cases, the observed dust appears to be dominated by small grains lifted at relatively low speeds, consistent with gentle gas drag from sublimating ice rather than a catastrophic explosion. Why is this surprising? In the classical picture of solar system formation, there is a snow line, a distance from the young sun beyond which water and other volatiles could condense as stable ice in the protoplanetary disk. Inside that boundary, temperatures were thought to be too high for exposed ice to survive over billions of years. Small bodies there should have lost their volatiles, leaving behind mostly dehydrated rock. The main belt lies near or just inside the traditional snow line estimates, so the discovery of bodies that seem to retain and periodically expose water-ice challenges the simplest versions of that story. Main belt comets therefore occupy a scientifically powerful middle ground. They look like asteroids in their dynamics, but like small comets in their behavior. They hint that the early inner solar system may have been more water-rich than once assumed, or that ice can survive for very long times when buried beneath insulating layers of dust and rock. Each new main belt comet identified adds another data point to the emerging picture, a main asteroid belt where dry rock and hidden snow coexist, and where the boundary between asteroid and comet is not a sharp line, but a continuum. On the surface, a main belt comet looks like any other small asteroid, an irregular, dark rock, coated in dust, quietly orbiting between Mars and Jupiter. But inside, some of these bodies carry a secret, pockets of ancient ice that sometimes wake up under the sun. Imagine slicing one open. In cross-section you'd see a crust of rock and regolith just a few meters thick, broken by fractures and voids. Beneath that insulating blanket, in some objects, lie reservoirs of water ice mixed with dust, leftovers from the early solar system that never fully dried out. For most of the orbit, that ice sleeps. Temperatures are low, sunlight is weak, and the dusty mantle acts like a thermal shield. As the object approaches perihelion, the physics changes. Heat from the sun begins to penetrate the upper layers. If a small impact, a landslide, or a crack has recently exposed fresh ice or opened a pathway to the subsurface, that buried volatile can begin to sublimate. Molecules of water vapor seep through pores and fractures toward the vacuum of space. On their way out, that gas drags fine dust grains with it, lofting them just above the surface. Seen from far away, that slow, persistent outflow blurs the object into a faint coma and sculpts a dust tail aligned with the orbit and the pressure of sunlight. This is classic comet physics, playing out in what we once thought was a purely rocky region. The key to making it work at main belt distances is time and insulation. Over billions of years, impacts and micrometeorite bombardment build up a lagged deposit of dark dust and rock that protects deeper ice from direct heating. Only where that armor is locally breached can sublimation restart. That is why the activity of many main belt comets appears episodic and localized rather than global and continuous. Not every dusty, tailed asteroid is powered by ice, though, and separating genuine sublimation from other mechanisms is one of the central challenges in this field. Sometimes, a one-off collision is enough. A small impact can blast a cloud of debris off an asteroid, creating a short-lived dust plume or trail that, in images, looks very much like a comet tail. In these cases there may be no gas at all, just inert rock fragments expanding away from the impact site. The activity fades as the debris disperses along the orbit, and it does not recur at the next perihelion. In other cases, the engine is rotation. Sunlight heats an irregular body unevenly. As it radiates that heat, tiny imbalances in thermal photons produce a net torque, the YORP effect. Over millions of years, that torque can spin some small asteroids faster and faster. If the spin period becomes short enough, centrifugal forces can overcome the weak gravity and cohesion holding the body together. Material sheds from the equator, or the object fragments into a cluster of pieces, releasing dust into space. The result can be multiple narrow dust streams, arcs, or a cloud of fragments, visually dramatic, but again, not necessarily involving any sublimating ice. So how do we know when a tailed asteroid is truly a main belt comet? Observers look for patterns and physical clues. One of the strongest is recurrence. If an object becomes active near perihelion, then quiets down, and then turns on again at nearly the same point in its orbit years later, that strongly suggests a thermal trigger rather than a single impact. The periodic activity of objects like 133P or else Pizarro is one of the cornerstone arguments for buried ice in the main belt. Another clue is the morphology and evolution of the dust. A slowly produced, broad dust tail that develops and fades in step with changing solar distance is more consistent with steady gas drag. In contrast, an impulsive impact or rotational breakup tends to create sharp, filamentary structures, multiple plumes, or fragment trains whose motion can be modeled without invoking gas at all. Combined, these observations have led to a working picture in which main belt comets are hybrids. Dynamically, they belong to the asteroid belt. Their orbits are stable, low-eccentricity paths between Mars and Jupiter, maintained over long timescales. Physically, at least some retain pockets of volatile ice protected beneath insulating regolith. When that ice is exposed or tapped by fractures, the body briefly behaves like a small comet, developing a coma and tail driven by sublimation. When the exposed patch is exhausted or reburied, the object returns to its dormant, asteroid-like state. This dual nature is exactly what makes main belt comets scientifically powerful. They prove that water ice can persist in the inner solar system longer and closer to the Sun than classical models once allowed. They hint that the boundary between wet and dry regions in the early protoplanetary disk was not a sharp line, but a blurred, complex zone where icy material was mixed into bodies we once assumed were entirely rocky. And they remind us that even today, between Mars and Jupiter, the story of water, rock, and sunlight is still unfolding on worlds no bigger than a mountain. Even in the crowded stone belt between Mars and Jupiter, the story of water is written into the rocks. When astronomers first mapped the main asteroid belt, they imagined it as a mostly dry, rocky population, the leftovers of a planet that never formed, baked inside the early solar system's snow line. But over the last few decades, meteorites, telescopic spectra, and now main belt comets have forced us to redraw that picture. The belt is not just stone. Hidden inside many of those dark fragments is water, sometimes locked into minerals, sometimes preserved as genuine ice. We see the chemical fingerprints of this story most clearly in carbon-rich asteroids and the meteorites they send to Earth. Carbonaceous chondrites, especially the Ci and Cm types, are filled with hydrated minerals, silicates that have reacted with liquid water in the past. Some even contain tiny veins of once liquid water that percolated through their parent bodies. When we measure hydrogen isotopes in those meteorites, the ratio of deuterium to hydrogen is surprisingly close to that of Earth's oceans. That simple number tells us something profound. Material with ocean-like water exists, and likely formed, in the same broad region as the present-day asteroid belt. Main belt comets are the missing link that turns those chemical clues into a living process. Instead of just fossil evidence in meteorites, they show us ice that is still there and still active. Their orbits are indistinguishable from ordinary main belt asteroids. Semi-major axes in the belt, modest eccentricities and inclinations, long-term stability between Mars and Jupiter. Dynamically, they belong to the inner solar system. Yet when they move closer to the Sun, some of them grow a faint coma and a tail, exactly as a classical comet would. That behavior only makes sense if pockets of volatile material, most likely water ice, have survived just beneath the surface. For billions of years, a dusty mantle insulates that ice from direct sunlight. Then something happens, a small impact, a landslide triggered by spin-up, or the slow opening of fractures as the body's interior expands and contracts with temperature. Fresh ice is exposed or brought closer to the surface. Sunlight penetrates a little deeper. Water begins to sublimate, gas seeps outward through pore spaces, and dust is lifted away, forming a tenuous, comet-like halo. The fact that some main belt comets turn on repeatedly, at roughly the same point in their orbit near perihelion, is crucial. A one-off dust cloud could be explained by a collision. Recurrent, perihelion-linked activity points to a thermal engine, buried ice responding to sunlight in a predictable way. In several cases, that activity is tied to specific asteroid families in the outer belt, suggesting that entire parent bodies in those regions were once ice-rich and later shattered, leaving fragments that occasionally vent. All of this feeds directly into one of the most important questions in planetary science. How did Earth get its water? We know the early Earth was hot and violent. Some primordial water may have been incorporated during accretion, some may have been lost, and some must have arrived later. For a time, distant comets were the favorite suspects. But isotopic measurements complicated that narrative. Many Oort-cloud comets have deuterium to hydrogen ratios significantly higher than Earth's oceans, making them a poor one-to-one match. By contrast, The water bound up in carbonaceous meteorites and inferred from the compositions of C-type asteroids is much closer to terrestrial values. In that light, the existence of icy bodies on stable mainbelt orbits becomes more than a curiosity. It is direct dynamical evidence that water-bearing planetesimals can live and stay in the same neighborhood as the bodies that eventually became Earth and the other inner planets. You no longer have to bring all of your water from the far Kuiper belt or Oort cloud. Some of the plumbing is already inboard, in the belt itself. The most realistic picture emerging today is a mixed story. Earth's water inventory likely reflects internal processes and volcanic outgassing from its own mantle, impacts from water-rich asteroids and their fragments, and perhaps a smaller, complementary contribution from classical comets. Mainbelt comets occupy a key niche in that story. Chemically, they belong with carbonaceous, water-bearing asteroids. Dynamically, they demonstrate that ice can be preserved for billions of years in the belt. Physically, their episodic activity shows how that ice can be exposed and mobilized. When their orbits are nudged, by resonances, by slow thermal drifts, some of those icy fragments can cross paths with planets. Each impact is destructive on the local scale, but on geological timescales it's part of a delivery system, scattering water and organics across young planetary surfaces. And this isn't just about our solar system. If belts of mixed rocky icy bodies are a natural outcome of planet formation, then analogues of main-belt comets may be common elsewhere. In other planetary systems, similar populations could act as couriers, shuttling water and carbon-bearing molecules inward to rocky worlds. Main-belt comets, in that sense, are local examples of a potentially universal mechanism, stones in the temperate zones of planetary systems that still remember the cold. When we point a telescope at a faint, dust-tailed object between Mars and Jupiter, we're not just catching an odd asteroid in a rare mood. We're watching evidence that water has always been woven into the inner solar system, hidden in the shadows of rocks, waiting for a moment in the sun. In many ways, main-belt comets are the most elusive members of the small body family. They do not blaze across the sky like bright, long-period comets, and they do not stand out as dramatically as large near-Earth asteroids. Most of the time, they look like any other faint point of light in the belt, until, for a brief part of their orbit, a whisper of dust gives them away. The challenge begins with what they are. Main-belt comets are small, dark objects, often only a few kilometers across. Their activity is typically subtle, a thin dust coma, a short tail, a slight softening of their image compared with a star. And even that weak activity usually switches on only near perihelion, then fades again. If you do not look at the right time, with enough sensitivity, you simply miss it. This is where modern sky surveys become essential. Wide-field telescopes that repeatedly scan the ecliptic can now track hundreds of thousands of asteroids night after night. By stacking images and comparing how individual points of light change over time, software can flag objects whose appearance becomes just a bit more extended, or whose brightness profile no longer matches a clean stellar point. In that sea of data, a small fraction reveal the telltale signs of dust, the first hint that a normal asteroid may be hiding ice. Once a candidate is identified, the work passes to larger, more precise instruments. Follow-up observations with big ground-based telescopes can measure how much dust is being released and how quickly the activity evolves. If conditions allow, sensitive spectroscopy is used to search for faint gas emission lines, a difficult, but powerful test of whether sublimating water or other volatiles are present. Just as important is patience, watching the same object over multiple orbits to see whether the activity recurs at similar distances from the Sun, strengthening the case for a thermal, ice-driven engine rather than a one-off impact. Looking ahead, main-belt comets are natural targets for dedicated spacecraft. One class of mission concept is a fast flyby, a probe that sweeps past an active object in the belt, mapping its surface in high resolution, measuring its temperature, imaging jets and dust sources, and sampling the dust environment with an in-situ analyzer. A more ambitious step would be a rendezvous or even a sample return mission to a main-belt comet, bringing back material that formed and remained in the inner solar system, preserving the isotopic and mineralogical fingerprints of inner-belt ice. Each newly discovered main-belt comet, each carefully monitored light curve, and each future close-up mission adds a crucial piece to the bigger picture. How much water and volatile material was stored inside the asteroid belt, how it has survived, and how similar populations might operate in other planetary systems. Hidden among the stones of the main belt, These small, quiet objects are key to understanding where snow can persist in the inner architecture of a planetary system, and how that snow can one day help make worlds habitable. Saw a prompt for this segment. Cinematic 16:9 documentary shot. Nighttime at a modern mountaintop observatory, a large wide-field survey telescope under a smoothly opening dome, stars wheeling overhead. Cut to the control room, astronomers silhouetted against large screens filled with star fields, one faint moving point showing a tiny, emerging dust tail highlighted by analysis overlays. Transition into space, a realistic main-belt comet, a DAC, irregular rock with a very thin dust coma and short tail, drifting among countless other asteroid fragments between Mars and Jupiter. A sleek robotic spacecraft streaks past, slowly panning its camera across the active surface while fine dust particles stream by. Realistic lighting from the distant sun, high detail, no on-screen text or logo. In the textbooks, the main asteroid belt is often drawn as a band of dry, silent rocks, a rubble zone between Mars and Jupiter where planet building stalled and then froze in place. But when you look more closely, the picture is not quite so simple. Hidden among the DAC boulders are a few, rare objects that break the rules. Most of the time they are indistinguishable from ordinary asteroids, small, faint points of light on stable, belt-like orbits. Then, as they approach the sun, something changes. Dust begins to lift from their surfaces. A fragile coma forms. A thin, sunward-ejected tail stretches along their orbit. For a brief season, a rock behaves like a comet. These main-belt comets remind us that the belt is not just a graveyard of stone. It is a repository of ancient ice, sealed beneath insulating dust since the solar system was young. When impacts, fractures, or slow landslides expose that buried ice, sunlight can turn a quiet object into a source of dust and gas, proof that water never belonged exclusively to the distant outer regions. In that sense, main-belt comets sit on the boundary between worlds we thought we understood. They connect the dynamics of the inner solar system to the chemistry of the outer. They link the story of resonances, collisions, and slow thermal forces to the story of where Earth's water, and the water on worlds like it, may have come from. So when we imagine the main belt now, we don't just see a ring of inert stones. We see a landscape where ice still survives in shadowed interiors, where a handful of small bodies occasionally remember their colder origins. For a little while, they grow tails, and the stone belt reveals that it has been carrying traces of snow all along.